Hello and hello everybody. How's everybody doing today? I hope you're doing well. Doop 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 doop. Sound check. Good. Alright. Earlier today I was having some audio sync issues. I actually had to interrupt the lecture that I just had to fix the audio delay because it was a second and a half when I first started the stream, and then at some point I guess YouTube realized, "Hey, that's not such a great audio delay." So it readjusted it on me, and I'm just like, "No, you just got to keep it consistent, man. I don't care what the delay is, just as long as it's consistent, and as long as it's not like 5 minutes or something, you know." Anyway, yeah. Anyway, that's all that. How are you guys finding the assignment so far? Oop. So this one, so there's a question in the chat. Why does CompSci not use Teams for live chatting, but we do? So the answer to that is because their stream hasn't been a problem. So generally speaking, my approach to these sorts of things is one of the minimal necessary intervention. So I deemed it necessary to move things onto Teams. At a certain point, if the in some sense the chat in 1MD3 is a bellwether to see how toxic chat is in general, I suppose. But and they didn't do particularly well today. But yeah, I'm probably going to consider stronger measures for them because today's chat was problematic. But that's actually the first time it's been problematic, so, you know, there you go. I think the problem we had with the moderation in the chat was more one of there weren't enough moderators. Like, there was only one guy who was moderating, so hopefully that's not the case again. But, you know, my idea is, generally speaking, the solution you want to go with to these sorts of problems is a conservative one. Like, you don't want to like go all the way in the opposite direction unless you have to, because, you know, there are good reasons to have public lectures, and, you know, I find also that the chat in the 1MD3 class is a little bit more free, a little bit more personal, and, like, I find it simulates a little bit better, like, the type of social atmosphere of a classroom. Not that you guys are, you know, necessarily bad at simulating a social atmosphere within the Teams thing, but, like, I think everybody fundamentally understands that's not the purpose of Teams, and that's the way it's being used. Like, it's very much more like direct line to the professor type thing, whereas, you know, I try not to like, my goal is not to restrict that social aspect any more than is necessary. Like, the general observation for this whole online learning thing in general, if you'll forgive the horrible phrasing of that, is that the social aspect is sorely lacking. You know, like, you guys are all stuck in rooms by yourselves. I'm also stuck in a room by myself. And to the degree that we can simulate the kind of social interaction that used to occur on a university campus, we should try to do so, because it's good for people psychologically. And I don't find that it necessarily interferes very much with me giving the lecture. So, you know, I like, to me, I understand there are good things about having the lecture, or the lecture chat on YouTube. However, the problem with this class is that, you know, there are sort of demonstrated and consistent bad actors in this class that have, you know, unless their names are on unless they are required to give up their names when they say something, they're not going to participate in a productive manner and try to, you know, ruin the experience for other people. So, you know, that privilege had to be removed. But just because your guys, I had to revoke that privilege, doesn't mean that the other class doesn't get their privilege maintained. Although, if things keep going the way they are going there, and, you know, I'm also aware of the fact that certain bad actors might be listening to this right now. So probably we'll have to move to Teams. It's not, I didn't want to, but we'll see how it goes. Average watch time is $1.43. Yeah, that actually has to do a lot with bots, but, you know. Also, the video isn't especially long yet. Concerning the median question in the assignment, should we flip it into a float or double? Should we truncate the answer in the median? Yeah, I received some communication about this through Piazza, and I'm terribly sorry. I think it should be a float. I'll issue a correction. I'll issue a formal correction at some point today. Yeah, like, that's okay. Thank you for expressing that, because I also miss the campus. Like, yeah, like, I miss hanging out with you guys for a few minutes after class, you know? I miss talking to a room. Right now I'm talking to a wall, you know? It's terrible. I miss the atmosphere. Like, you can walk around campus and like once an hour for 10 minutes. It's like Times Square, and then the rest of the time it's dead. It's amazing. I miss the cafes, you know? And I miss people talking about like philosophy in a cafe and hearing that going on in like one corner of the room. Like, yeah, it's sad. This is sad. What we're doing right now is sad. But there's an anti-mask rally on campus today. I don't think that that's a solution either. Uh, I do think I would be careful about the anti-mask people, not to throw the baby out with the bathwater there. They do make some points which are worth considering, right? Like many people have considered, you know, like a popular argument I hear from coming out of the States these days is, you know, the number of people that you would kill through, you know, the economic privation that's enforced by shutting down an economy might be greater than the number of people who would actually die of the virus. Stuff like that, like you want to listen to both sides of an argument every time, right? Because you never know if the other side has something that's important for you to hear. But as far as, like, with respect to, you know, masks themselves, it baffles me that people don't consider that universal politeness. So, in the juggler sequence, do we always round down for the next term? Yes, that's the definition of floor. So, when I ask you for floor, that's what I'm asking you for. So, there you go. Anyway, enough of a pity party. Let's talk about computers and stuff, because that's ostensibly the actual purpose of our meeting here today. So, let's talk about Shellsort. We were talking about Shellsort. We were talking about Insertion Sort and Bubble Sort, and I was explaining how Shellsort is an actually, like, a really good algorithm that is deployed in actual commercial settings. Like, this is a thing people actually use. Shellsort has a number of advantages over some of the other sorting algorithms that you may have heard of, like Quicksort, because it's relatively memory efficient, and it doesn't use the call stack, which is an element of memory efficiency. This makes it ideal for small applications, like embedded systems. So if you want an efficient sorting algorithm for embedded systems, you should pay attention to Shellsort. And given that you guys are primarily either people interested in embedded systems or robotics people who should always be interested in embedded systems, you should consider this to be a good one for you. So the idea with Shellsort is that we are dividing our array into subarrays, sorting those subarrays, and then putting them back in the original array. The mechanism by which we break our array into subarrays is called interleaving. So subarrays are formed by taking an element, skipping h elements, and taking the next element, and then skipping h elements, taking the next element until you run out of elements. I've already talked about how the sequence of h values that you use is that actually affects your runtime in interesting ways. So let me just bring up the Wikipedia article for Shellsort, because there's some interesting stuff in there. But yeah, anyway. So this is a visualization of the interleaving process, and you'll notice that I fixed the number. I fixed the number since last week. But so you take 0, you count 1, 2, 3, 4, 5, and then you take 6, 1, 2, 3, 4, 5. Another way of thinking about that is to take your array and slot it in to any degree it overhangs 1 plus the HGap, and then cut off any overhang, put it underneath, and sort of form a matrix out of that, and then take the columns. That's a sort of a geometric way of thinking about it. But in this particular case, we get h plus 1 different subarrays, which we can then... Obviously, this array is already sorted, so we don't have to do anything further, but this is the same array broken down with an HGap of 3. So, you know, it's element, skip, 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 element, skip, 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 element. But the interesting thing to note is that there's a reason I color-coded this, right? When you're finished collecting your first subarray, you start counting the next subarray at the next element after the first, and then you skip the same number of elements. So hopefully that's reasonably clear. Good. Good. People seem to get the idea. So, once we have our subarrays established, we perform insertion sort on each one of them and then put the elements back into the original array. So this is interesting. This is a sorting algorithm that uses another different sorting algorithm. So insertion sort is a subsort of Shellsort. if you can wrap your noodles around that one. So the reason that you would the reason that we use insertion sort on the subarrays is that insertion sort's runtime is proportional to the length of the array. So, and it's a non-linear relationship. So sorting six arrays of size 2 is less time than sorting one array of size 12 with respect to the insertion sort algorithm. It takes less time. The thing isn't completely sorted when you're finished with that step, but we'll see how that works out. Once all of the subarrays that have been extracted with a particular HGap have been sorted and replaced for one H value, we say that the array is H sorted. So if we were to take all of these subarrays, sort them, and then put them back into the array, we would say that this array is H sorted. Or in this case, since H is 5, we would say it is 5 sorted. A little bit of terminology. The success of Shellsort hinges on the fact that smaller H sortings do not disorder large ones. So if we have an array and we H sort it by 10, let's say, so we perform the sort operation, the array is now 10 sorted. If we then go into that array and perform a 5 sort on it, it's still 10 sorted at the end of the 5 sort. That's an important property. If sorting with an HGap of 5 disrupted the sortedness according to a gap of 10, then Shellsort as an algorithm would not work, because you would be disrupting previous sorts. So fortunately, that's not the case. Or maybe it is for particular values, but I don't think so. So, for example, if an array is 40 sorted and we 14 sort it, the finished array is still 40 sorted. Yes. As long as the last H value is 0, which is just insertion sort, the array is guaranteed to be sorted. So, the logical conclusion, if we want to move from larger HGaps down to smaller HGaps, the logical conclusion of that is that we end with an HGap of 0. That means that we get one subarray, which is the entire array, right? And so it's like take one, skip none, take one, skip none, take one, skip none. That gives you back just the array. And since we are sorting based on insertion sort, that's just running insertion sort. Sorting with an HGap of 0 means running insertion sort. The cool thing is, though, if the previous HGap that you ran was 1, so you take every other element, then no element will be out of place by more than 1, right? Which is interesting, because where you really run into bad runtimes with insertion sort is when you have to pass back a whole bunch, like this example here, when you have to pass the 3 back almost all the way back to the beginning of the array. That's where you run into long runtimes. But if no number is if it's guaranteed that no number is more than one place in the array off of the position that it should be, then that substantially decreases the amount of time it takes to run insertion sort. Substantially decreases it. The trick is, of course, that it has to be in that. It has to be, 2 sorted or 5 sorted, and you can imagine that that relationship is held throughout throughout all of the various H sortings. How are you guys doing with this? Are you guys getting this material? I know it's a little bit abstract and mathematical, but hopefully you're doing okay with it. I'll give you guys a moment. So, ooh, I can see I cut off my, aw, man, I'm having the worst time with diagrams. Incidentally, if anybody's interested in these diagrams, I made all of these diagrams with a software tool called GraphViz. It's kind of cool. You code, you can encode these. You can type out these diagrams like they're programming code, and in a sense, it is a type of programming code. This is what this diagram looks like in GraphViz, which is kind of cool. But yeah, let's see. Cool. Yeah, if you guys have been noticing with this particular set of slides, I haven't been including, like, the algorithm encoded in C. And the reason for that is, well, I imagine you found out the reason when you took a look at assignment 2. A lot of these algorithms, I think it's a really good exercise to take these algorithms from the description I'm giving you and actually, come up with a version in C that works. So that's why insertion sort, bubble sort and insertion sort are on assignment 2. I was actually originally going to put Shellsort on there as well, but it turns out that Shellsort is a heck of a lot easier once you know dynamic array allocation, which is something that we're going to talk about when we talk about pointers. We're going to talk about dynamic array pardon me. Like the problem technically with doing Shellsort with your current level of understanding of C is how do you allocate space in memory for an array if you don't know the size of the array? So far, all of the sizes, like all of the arrays that we've been doing so far have been hard-coded with respect to the size, or, you use a define statement. All that is a way to generalize hard coding. It's not, like, you're not actually producing dynamic arrays. And the reason we're not covering dynamic arrays inside of this particular set of slides on arrays is because pointers. Everything comes down to pointers. So we're going to talk about pointers quite soon. if you're interested in taking a look, I don't think this is actually going to be a problem, but I have like a first draft up of the set of slides I'm currently working on about pointers. I know I should have it done for Tuesday, but um, you know, life kind of works in mysterious ways. I kind of beat myself senseless with this particular set of slides, and I ended up with 4 lectures worth of material, so I'm going to use it, gosh darn it. Anyway, why would you care about that? Stop talking, Nick. Anyway, so this is how Shellsort works visually. So let me just blow this up for you guys. Sorry that got cut off. The number of examinations is 3. So our first, we're sorting here. This is the same array that we've been sorting this whole time. Our sort here, we begin with an h equals 2 sort. We then move to an h equals 1 sort. Sorry, the label is displaced. And then we do the h equals 0 sort. So our HGaps are 2, 1, and 0, which, you know, illustrates the concept pretty well, I think. Even if it's not like an optimal arrangement of HGaps. On an array this small, it's like you might as well just insertion sort it, really. But anyway. It's a learning example. So anyway, for the h equals 2 subarrays, the first one you take is 9, 1, 6, right? That's your subarray. The next one will be 4, 7. The next one will be 7, 3. So if we perform insertion sort on 9, 1, 6, and incidentally, you don't have to put the code that is insertion sort inside of your quicksort algorithm. Your insertion sort algorithm does not need to physically go into your shell sort algorithm. You can just call it. That's the purpose of function calls. If you perform insertion sort on 9, 1, 6, you get 1, 6, 9. That requires 2 swaps and 3 examinations. So then you can put it back in the array. And now it's sorted. And you can see this is green now because it is 2 sorted, that section of the array. The next one you pull out is 4, 7. That is already sorted. Examines it once, swaps it no times. Put it back. 7, 3. That becomes 3, 7. 1 examination, 1 swap. You put it back. This is now a 2 sorted array. And those of you who are very observant will notice that this array is actually only one swap removed from being a completely assorted array. In fact, because of the particular nature of this array and the fact that humans are not, nearly as random as they think they are, I constructed this array just by punching numbers on my keyboard. I didn't use a random number generator or anything. It seems I ended up being biased towards HGaps of 2, because when we perform the H1 sort, which is every odd element, which is already sorted, and every even element, which is already sorted, no swaps are actually performed, although the number of examinations has increased because the number of the size of the subarrays has increased. So after performing these sorts, the array is now guaranteed to be 1 sorted. So I should make one point particular though. Although no swaps were performed at the h equals 1 sort, we couldn't have known that about the array ahead of time, right? You can't skip HGaps once you have, decided on particular H values. You can't skip them once you decide on them based on information in the array, because, you don't know the information in the array until you've examined it in this manner. So, yeah. Anyway, once that's the case, we begin the H equals 0 sort, which is just regular insertion sort, that performs 1 swap, although it performs 7 examinations. I have a question. Boop, boop. There we go. I'd like my slides to line up. Doop. Is there any way to know which is the optimal HGap, or do you have to run through it and find out? So, the answer to your question is a little bit complicated. I want to talk about the concept of an optimal sequence of HGaps. With respect to any particular array, you just have to run through it. To the more general question of, is there a more efficient sequence of HGaps, I want to refer you to the Wikipedia page that I forgot that I was looking up. So this is an animation of Shellsort going on. I didn't find this animation to be particularly useful, but, you know, it illustrates the concept, I suppose, in general terms. So, on Wikipedia, there are a number of proposed HGap sequences. As I said in the previous lecture, the sequence of HGaps which we use is actually like various researchers into algorithms will make various proposals for HGaps. Generally speaking, they'll back them up with mathematical analysis to try to demonstrate that their sequence of HGaps is superior in some way to the sequence of HGaps that have gone before it. If you notice, so in general, you can think of this list as a sequence of HGaps that improves with time. So some of these have mathematical formulae which predict their next values. The most recent one is interesting because it's experimentally derived. So there's no theoretical model which currently accounts for these HGap sequence. However, you know, it's considered to be a good one, or at the very least a recent one. What's also very interesting is that the worst case time complexity of these algorithms is actually dependent on the sequence of gaps that you use. So it can be mathematically demonstrated that this one, for example, 109, 41, 19, 5, 1, that gives you a big O, that gives you a complexity of n to the power of 4 over 3, which is pretty good. It's like somewhere between linear and n squared, which is not bad. It's an improvement over n log n, I think. Anyway, so there's really what the best sequence of HGaps is an open topic of research. Although it hasn't, there hasn't been much progress on it since the year 2000, at least according to Wikipedia. It's probable that there have been other papers published that just aren't represented here. But yeah, it's an active area of research. So good question. Thank you for the question. Anyway, let's continue to talk about it. So, in terms of the analysis here, if you remember, for insertion sort, the number of swap operations we needed was 13. This is the same as bubble sort. You remember I considered it irreducible to some degree because insertion sort can only remove 1 degree of disorder per swap. Shellsort can remove many degrees of disorder per swap because the swaps it's making are across the entire array. So in Shellsort, the total number of swaps that are required is only 4. 4. That's crazy talk. even the total number of examinations is only 17 compared to the well, it's actually the same as the total number of examinations for insertion sort, but it's, certainly less than bubble sort. So we have reduced the number of swap operations, but the number of examinations has remained the same. That's crazy, considering the amount of overhead that we have to do. But the thing is, the interesting thing about this is, if you configure your algorithm correctly, you can vastly minimize the amount of bookkeeping that you have to do to create and maintain these subarrays by using pointer arithmetic. But yeah, well, vastly might be overstating it, but you can do that efficiently as well. Anyway, while the previous slide implies the subarrays are instantiated separately from the original array, this does not need to be the case. Shell sort may be performed without allocating new memory beyond the swap space insertion sort uses. You can sort things in place if you have a insertion sort algorithm which, basically, if you make the number of if you build into your insertion sort algorithm, if you generalize insertion sort so that it can sort, basically so that you can modify how many places in the array it skips to get to the next element. In our regular insertion sort, the comparison is between adjacent things. If you modify it so that the comparison is between elements of configurable distance from each other, then you can actually you don't actually have to extract out the subarray, allocate new memory to it, and then perform it there. Since insertion sort is an in-place operation, shell sort can also be an in-place operation. Which is, again, why it's preferred for applications like microcontrollers that are highly memory restrictive. As I was saying, the worst case analysis for shell sort is highly dependent on the HGap sequence. Early versions in the 60s are guaranteed to be no worse than big O of n 3/2. The best versions we have now, for which we know their characteristics, right? Where is the thing that I had? Boink, there we go. So, eventually the idea is probably algorithms researchers will arrive at what the worst case complexity is of these guys. But, the most recent ones that we have good results for put it at n to the 4/3. So that's shell sort. I hope, please, if anybody has any questions about that, please ask them now. I'll give you a moment. I'll stretch my arms. There we go. I'll give you guys a moment to ask a question. Also, this is a great time to like and subscribe this video. If you'd like more content from this creator, then please like and subscribe. Sharing this video is the best way to get this video content to all the people who might want to be interested in it. If you think my content is good, then like and subscribe and share with your friends. Oh yeah! Take a shameless plug break. There's a question. How do we determine which H to start with? Generally speaking, you use one of these. Which one of these you use? To some degree it doesn't matter, but just pick one that's good, I guess. If we ask you to implement shell sort on a future assignment or something like that, we'll tell you what HGap to use. So you don't have to worry about like picking your own. Picking your own HGAPs, as should be demonstrated by this long list of algorithms researchers, is a non-trivial a non-trivial operation. So we're not going to expect you, poor humble undergrads, to completely derive a new Shellsort HGap sequence. Although, you never know. Maybe you guys come up with something that like completely beats the pants off of everything that's gone before. You don't know. It might be. But you know, it's unlikely. It's also possible that one of you guys has like the sufficient mental configuration to solve some of the Millennium problems, but the probability that any one of you has that is reasonably small. But that's the beautiful thing about human beings, you know? Shell was a person. Oh, is that true? Is it named after a person? Shell's method. Oh, yeah, there you go. Yeah, published by Shell. Shellsort. That's a person. Oh my god. I got this far too without reading what was in front of my bloody face. Yeah. There you go. Yeah, Tim Sort is named after a person named Tim, so I suppose Shellsort. Why not? So anyway. So you might be saying to yourself, okay, this is a lot of bloody time that we've spent explaining how to sort things. Why is it so bloody important that we know how to sort things? That should be obvious to you by the time we are finished talking about binary search. For those of you who are in Parker's tutorial class, which happened yesterday, I believe Parker did some stuff on binary search. So this will be the official lecture notes version. Hopefully you will have had a good introduction to it. So, in order to talk about search algorithms, we should first define them. So, searching algorithms, generally speaking, you're trying to find things, obviously. Given a data structure composed of elements and an element to search for, a search algorithm tests for the presence of a searched for element in the data structure. And to those of you who think that search algorithms are like this little toy example that is only useful inside of the context of, classes you take in university, I've got one word to say to you, you doubting Thomases of the world. Google. The output can either be true or false. You can either have a true-false value, which indicates the presence of the thing being searched for, or you can return the index of the searched for element. That might be more useful in some circumstances, but there are plenty of occasions when you just need to know whether a thing is in a thing. Search algorithms may be applied to many diverse types of data structures, but we're going to focus on arrays for now because, this is the lecture slides on arrays. The most straightforward approach is linear search. In linear search, you start at the beginning. You start by comparing the first element of the array to the thing you're looking for. If it's the thing you're looking for, great. If not, you move on to the next one, and you do that until you run out of elements. It's very simple. You might even consider it a brute force solution, a brute force algorithm. Brute force algorithms, that's a term that you'll probably hear in your algorithms class. That's like a simple algorithm that performs more calculations than might be necessary because you didn't want to put enough thought, you didn't want to put the thought into coming up with a better algorithm, essentially. So bubble sort is a brute force algorithm if you compare it to something like Shellsort. So the algorithm returns true, or returns the index, as soon as the item it's looking for appears in the array. If the end of the array is reached before the item is found, then it returns false. The worst case complexity of linear search is big O of n. And this happens if the item isn't present. Because, you don't know that the item isn't in the array until you've checked every element in the array. Because if you had that type of foreknowledge, then, you could just use your mystical powers to determine whether the thing is in the array or not. The average position of the sought-for element is in the middle, assuming uniform randomness. So if you assume that there's an equal probability that the item you're looking for is any particular item in the array, then the complexity there is n divided by n over 2. But of course, that's a constant term, so it's still big O(n), right? Yeah, though this is still big O(n) because we only care about the power, not the constant. We have to use linear search if we can't assume anything about the data. So, if it is true that the element we're searching for could be anywhere in the array, and there is no relationship between the different elements in the array, then we have to use something like linear search. However, if we know something about the array, we can use a more efficient algorithm. So in algorithm design, if data has known properties, then we can use this information to come up with better algorithms. So this is sort of this idea of invariance. A little bit earlier we were talking about this idea that part of the purpose of applying an algorithm is so that you can make certain mathematical claims about the data. One of the mathematical claims you can make about an array is whether or not it's sorted. It is often the purpose of sorting something is so that you can make the mathematical claim that it is sorted, so that you can apply algorithms which assume sortedness of the data, which are more efficient than algorithms which are operational despite the sortedness of the data. I know that's a long-winded way of talking about it, but so anyway, binary search is an algorithm that has a worst-case complexity of log base 2n. Now, if you remember what functions look like, an polynomial function like n squared increases like that. A linear function increases linearly, and a logarithmic function increases like that. You get very small increases in the amount of runtime for very large data sets. We're going to be looking at this. Rather than looking at each item, binary search narrows the field of search iteratively until the value is found or not. So because the field of search is in order, we can use that orderedness to so rather than conceptualizing the search as examination of each individual element in the list, we can examine the we can take the array as a field of search and narrow that down. We can exclude large portions of the array in which we know that the element we're looking for isn't going to be found, fundamentally. So, I know we don't have much time left, but here we go. So this is the procedure for binary search. Let's say we are looking for x in the array A. First, we create two variables to keep track of the search range. So A will be the upper bound of our search range, and B will be the lower bound. Or, sorry, strike that, reverse it. A is the lower bound, and B is the upper bound of our search window. Of course, upon initial inspection of the array, the entire array is a valid search region, so A will start off at 0 and B will start off at 1 minus the length of the array, which is, or if we are equating these two indexes of the array. We then examine the number at m is equal to a plus b divided by 2, and you take the floor of that. Floor is just truncating, getting rid of the decimal place. Rounds down always. If m, a, or b is equal to x, then we have found x. It is in the array. If this number is less than x, we know that x must be at a higher index. So if m is less than the number we're searching for, then we know that the number we're searching for has to be in the portion of the array that is greater than m. Conversely, if m is greater than the value we're looking for, we know that the value we're looking for must be in the portion of the array that's less than m if that value is in the array, if it's in that subarray. So, having established what half of the array the value we're looking for has to be in, we can move the bounds of the window that we're looking in to the midpoint. We either move the lower bound up or the upper bound down to divide the search space of this algorithm by half in one step. Here is a visualization of how that works, and I know we're just about out of time. So A is red, B is blue, the M is in light blue. So if we're looking in this array for the value of 84, I mean, if we just look, we can see it's right here, but the computer just can't just look, right? That's the whole thing about computers. So 49 is less than 84. Therefore, we know that 84 has to be in the upper section. So we can take A and we can move it up. We then take the next midpoint, which ends up being 78. 78 is still less than 84, so we know that the value 84 must be in this section of the array. We can then examine that midpoint. The midpoint here is 93. That's greater than 84, so we know that it must be in the lower half of the array. Eventually, we narrow in on 84 itself, and we have found it, because it is in the array. If you reach the point where the bounds on the array are, pardon me, if A and B are sufficiently close together that A, B, and the midpoint are contiguous elements of memory, that is to say, they're adjacent, then you know that all of you've searched everywhere that it is possible for this value to be. So if you don't find it, then you haven't. Then the search returns that it hasn't been found. Anyway, that's about as much time as we have for today. Thank you very much, everybody, for listening to me pontificate about all this stuff. We shall continue this on Thursday, and we will talk about pointers on Thursday, because I'm pretty sure I can't stretch out 2 slides to be an entire lecture, even if I tried. Pardon me. Anyway, have a nice day, guys. Go get some lunch. I'll stay around a little bit to answer your questions if you have any questions. But that's it. Question. What if the key is at the beginning or the end? Well, it depends on how you write your binary search. In this particular version of it, so there are a couple of versions of binary search depending on, like, how you want to deal with the upper and lower bounds. In this particular version that I've written on the slides, you're examining M, A, and B to see if they're equal to X. So if X were, for example, in this example, 2, we would find that on the first pass, right? However, there are some binary search algorithms that don't check A and B to see if they are the value that you're looking for. And, that means that they'll just, narrow down and narrow down until A divided by B over 2 is equal to 0. in which case m becomes 2 here, and then it finds the thing that it's looking for. So that's what it would do in that case. Hopefully that's an answer to your question. I think it is. If there are any other questions, please ask them now. Cool. Anyway, have a nice day.